Jai Hind everyone. I am going to teach you about forces on submerged bodies. Hello, I am Nikita Jaiswal from Civil Engineering Department, Ajay Kumar Garg Engineering College. So the topic is forces on submerged bodies. So when we talk about submerged bodies, what concept and what thought actually came into our mind that there will be a flow and some type of object must be submerged on it and some particular type of forces will be acting on particular object. Okay, so that's the same concept we are going to study, but with some analytical forces, some coefficients we are going to discuss. So let us suppose when we talk about submerged body, okay, then two types of forces are actually acting on particular body. Let us suppose this is a body and this is submerged in, let us suppose this is a flow coming in this direction, and this flow is having a velocity of u infinity. Let us suppose this u infinity is simple stream velocity, okay, and this particular object is submerged in that particular flow. So what you will say that obviously when that particular fluid comes in contact with this object, there are two types of forces will come. Okay, the first one is shear stress, obviously tangential to the contact, and a pressure force, or you can say a normal force, which will be acting on this particular small area. Okay, so two types of forces will be there when there is a contact between upstream flow or a streamlined flow and any object. Okay, so this type of these two forces will act. The first one is shear stress and second one is normal to the particular surface, that is the normal stress, or you can represent as a small p. Okay, so when we apply this forces for the entire object, okay, this force is actually acting on, I am showing you this small p and this rho, this is actually acting on a small area. When we integrate it, obviously there will be total normal force and total shear force, obviously. But when we talk about horizontal and vertical force, okay, let us suppose I am taking a total of horizontal force in this direction. Let us suppose I am calling it as Fd, okay, and there is another force which will be acting upon the normal of the surface. See? So summation of horizontal forces will be called as your Fd, or you can say it as drag force. The summation of vertical forces you can call this as Fn or lift force. Okay, so let us suppose. So here we know what is drag force and what is lift force. Okay, so let us suppose when for take an example, when you travel through hills, and let us suppose you take a parachute and you slide over the air. So when your parachute comes down in vertical direction, what happens actually? There is a lift force. That atmospheric air is actually exerting a lift force over this parachute. Okay, so this type of force is called your lift force. Okay. And so this is just an example of parachute when we are talking about lift force. And the second, let us suppose drag force. See, whenever you move, you travel from a bicycle, let us suppose, okay, and whenever you travel, let us suppose in x direction, okay, so let us suppose the air is flowing against you, so that air will exert a pressure on you, so that force will be call your drag force, obviously. So this type of forces, drag force and lift force, actually we experience these forces on daily life, but we never thought of analyze it, we never thought of use or we never thought of its application when you are an undergraduate student. After studying it, after applying engineering on these concepts of fluid mechanics, you can use it for further applications. Okay, so drag and lift. Okay, if an body is submerged in a moving fluid, experience a resultant force. Okay, force R due to the interaction between body and the fluid. This is clear. The force on a body is due to wall shear stress, or you can see this shear is actually due to viscous effect. What is viscous effects? When the fluid is having some viscosity, obviously when that fluid comes in contact with an object, that forms a boundary layer over the object. Okay, so because of the boundary layer, because of the interaction between the particles of different objects, so this kind of shear stress acts. Okay, and the normal shear stress, you can say simply pressure due to the weight of fluid. Our interest is to learn how to determine the various forces on objects surrounded by a moving fluid. The drag and lift, again when we continue about this concept, the force that flowing fluid exert on a solid body can be separated into drag and lift components, as we talked already. So drag force, what is drag force? Is a component of fluid force that acts in the same direction as flow. And the lift force, what is lift force? This is the component of fluid force that acts in direction perpendicular to the flow. Here you can see in this particular diagram, there is an object and this object is submerged in particular flow. Okay, so there is an small, you can say small area, okay, in this pressure force and this shear stress is acting. Okay, and when we summarize, when we take integration of this small p and shear stress, okay, and then when we resolve this in horizontal and vertical direction, then we will get FD and FL. Okay, after resolving pressure force and shear stress, okay, and taking an integration of our entire body, you can take the formula for FD as integration of AB, that is area of particular object, will be equal to P equal to cos theta dA plus integration of tau W sin theta dA. So here what is AB? Is the surface area of the body, simple. And what is theta? This is the angular location of the elemental area dA on the boundary. Okay, whenever you take a small incremental area, what is the angular location of that particular incremental area or elemental area? So this is your theta. Okay. At a given point, pressure is normal to the surface and oriented theta to the horizontal. Shear stress is tangential and oriented at the same angle to the vertical. So how what you have done, just resolving after P and tau, you can get FD, and again after resolving P and tau in vertical direction, what you can get, this formula FL equal to minus integration of P sin theta dA plus integration of tau W cos theta dA. Okay. Now again, when a body is immersed in a moving fluid, experience a resultant force, what we have talked about already. Then the resultant force due to, this is a resultant force that is due to interaction between body and fluid. Okay, this is simple, drag in x direction, lift in y direction, and the resultant is R. Okay, so here you can see, the simple force, how we have written it as FD, the formula is written here, and for FL formula is written here. Okay, so both shear stress and pressure, both shear stress and pressure contribute to the lift and drag. Okay. So pressure distribution can be obtained experimentally using static pressure taps along the surface, but shear stress distribution, it is very difficult to obtain. Okay. So this formula we apply by taking many assumptions. Okay. Now we will talk about how this drag force and how this lift force acts, and what are the factors on which it depends. So let us suppose you are just walking, okay, and what you feel, the air pressure, it's almost negligible, because uh, when your velocity is very slow, okay, when you are just walking, your velocity is very slow, so the amount of drag force you are facing is somewhat little, okay. Let us suppose on the next step, let us suppose you are traveling on a bicycle, okay, then what you will experience, the drag force is, now you are experience the force of air or drag force will be more, okay. The next step, when you travel through a bike, okay, what you will face, the air pressure, the air force, or you can say the drag force is more. So on an average, on a conclusion, what you can say, that whenever the velocity is increasing, okay, whenever the Reynolds number uh, of particular body is increasing, that means the force, the drag force coming opposite will be, obviously will be on an increasing direction, okay. So you can say that drag force, okay, suppose fd is proportional to velocity, okay, you can say that. This is the first point. Now let us suppose you can say the area, okay. Let us talk about area, the area of object. See, I am just taking an example. Let us suppose this is a mobile phone, okay, and the air pressure, or you can say that the flow direction is in this direction, okay, perpendicular to this area of this mobile phone. So when I put this phone in this orientation, this object area, okay, the subjected area is more, obviously, so the drag force will be more on this particular object. But when we place this phone like this, and the moving fluid is in this direction, so the projected area is, you can say, this is less than this area, okay, so obviously the drag force will be less. So what you can say, that the particular drag force will also depends upon the projected area. So you can say this will also depend upon the surface area, okay. Now the next, this particular drag force also depends upon the fluid density or fluid viscosity, okay. So just take an example. When you are traveling in this environment, okay, in air, the drag force you are facing is different than when you swim in swimming pool or in water or in river, whatever situation. But when the media is different, when the media is air, what you can feel less drag force. But when you are traveling, when you are swimming in water, what you will face, more exert or more drag force. You are forcing, you are applying more power to come over that uh, that medium, okay. So what you can conclude, that that particular drag force will also depend upon the density of medium. So what our conclusion is, that this particular force is depend upon the three factors. The main is velocity, and the second is area, and the third is your density. So and also here this velocity is what is actually, you can say, body velocity, or also you can say the flow. This will depend upon the velocity of body, and also it will depend upon the flow velocity, or you can say stream velocity, okay. So I am putting an oblique and writing it as infinity. So when you write a formula, when you formulate a formula, what you will get as Fd equal to Cd, area, multiplied by rho u infinity square by 2, okay. So this is a formula for Fd, and now the formula for Fl, what you can say is as Cl, area, rho u square by 2. Here this is what, here Cd and Cl. Cd is coefficient of drag and Cl is coefficient of lift, okay. What is area? Obviously is the area of the body which is projected area, okay, of the body perpendicular to the direction of flow. Okay, perpendicular to the direction of flow. See, if the flow is in this direction, okay, and body is placed in this direction, so whatever the projected area is coming in the flow direction, that you have to take as capital A. Now the resultant force, what obviously the resultant force we know very well. When you know FD, when you know FL, obviously you can calculate this resultant force as root over FD square plus FL square, right? Okay, when we write formula for FD, the total drag formula, okay, we know very well this is the formula. It is integration of P cos theta dA plus integration of tau sin theta dA. Okay, here this term integration of P cos theta dA is actually pressure drag, or you can say this is form drag. Okay, and what is that? Tau naught sin theta dA, this is friction drag, or you can say it is a skin drag or shear drag. The relative contribution of the pressure drag and friction drag to the total drag depends upon the shape of immersed body, right? The position of body immersed in the fluid and fluid characteristics. That means what you can conclude from these 3 points. The first is shape of the immersed body. What I have taken already an example of a mobile phone, that do orientation when you put that particular shape in the direction of flow. So obviously, which kind of shape you are subjecting to a flowing fluid, that will affect the total drag force. And the position of body immersed in the fluid, what is the position? It is in inclined position, or it is in horizontal position, or it is in particular perpendicular position. So positions, or you can say the theta, what is the value of theta, that will further cause your FD. Okay, and what are the fluid characteristics? Obviously, when the density is more of fluid media, obviously then the fluid drag force will be more. Okay, here in this diagram you can see there is an horizontal, horizontally placed object, and here you can see, because the projected area is very low, here you can say the major contribution of force is due to shear stress only. Okay. Now here is a diagram, there is a figure of flat plate actually perpendicular to the flow. When the flat plate is you are placing perpendicular to the direction of flow, what will happen? What will happen? See, you can see how this streamlines of particular flow is moving in this direction. Okay, so this is actually shear stress. In this case, actually shear stress is like in this direction, 2 rows are going on up direction, 2 rows are going in down direction. Okay, the flow lines are separating from the bodies like this. So the streamlines, when the streamlines separate from any body, that point is called a separation point. Okay, you need to remember what is separation point, you need to remember what is wake zone. Okay, so here what usually we say, when the boundary layer get destroyed from any point, or you can say after the separation point, what actually happens, the wake zone is created. Okay, wake zone is created. So this zone is actually your weight zone. And what do you mean by this upstream and downstream? What upstream is simply the upstreams of this plate, and downstream is simply when we are talking about the zone which is downstream on the of the plate. Okay. So okay, I haven't yet talked about the actual application of drag and lift force. So just take an example. You have seen the airplane, how this airplane takes off. Okay, whenever airplane is runs over a runway. Okay, let us suppose this is an airplane. This is not looking like an airplane, but let us suppose this is running over an runway, and after some point this takes off like in this direction. What actually this aeroplane takes help of drag force actually. Let us suppose this air is coming in this direction. Okay, let's suppose the air is coming in this direction. So this air is applying a kind of drag force in that aeroplane. Okay, so what aeroplane does is take use of that particular drag force and that lift in this direction. Okay, also when that particular aeroplane that lands on a surface, then also to provide resistance to come to a stoppage point, also that take use of drag force. Okay, the drag force actually at that point provides a resistance so that the airplane stops at particular point. So this drag force and this, so there is another example. Whenever the automobile industry is okay, that then they design cars, okay, different vehicles. They design, let us suppose this is a car. Okay, so they design this particular area in a such a way that whatever flow is coming in this direction, this flow goes in very smoothly. Okay, so that there is a minimum amount of drag force, and that particular vehicle provide more power with less consumption of energy. Okay, less consumption of fuels. So you have seen the sports car also. Sports cars, what the production units of sports car, what they do, they try to reduce or minimize this portion, try to reduce more and more to minimize this particular area, so that the drag force, the exerted drag force and in that particular vehicles will be small. Okay, so this are the actually these are what we are going what we I'm trying to tell. This is are the more and more applications of drag force. There are n number of applications actually. Okay. So now we are going to discuss more and analyze how this forces can be calculated. So let us suppose this is an example 14.1 of fluid of your book R.K. Bansal, fluid mechanics. Okay, so this is problem of 14.1. Here you can, here it is written a flat plate. Okay, a flat plate 1.5 m cross 1.5 meter moves at 50 km per hour in a stationary air of density 1.15 kg per meter cube. Okay, here it is written as your u infinity is your 50 km per hour, and air density, okay, density is written as your 1.15 kg per meter cube. Okay, and the coefficient of drag and lift are also given. So this is 0.15 is your CD and 0.75 is your CL. Okay, area is also given. Determine lift force first, second is drag force, third the resultant force, and fourth the power required to keep the plate in motion. So there is simple case of flat plate. The area is also given, and in which the flat plate is kept is also the media, and the velocity of flowing fluid is also given. Okay, so what you have to do is simple apply your equation of force. Suppose here FL equal to CL area rho u square by 2. We know this formula. Here CL is your coefficient of lift, area is area of a particular object, rho is what, simple your density of medium. Okay, and u is what, free streamlined velocity, or velocity of, you can say the simple velocity of medium. Okay, so simply area of plate will be what, 1.5 cross 1.5, this will be equal to a 2.25 meter square. Okay, then the velocity of plate is given as 50 kilometer per hour. When you convert this 50 kilometer per hour, what you get is 13.89 meter per second. Simple. Okay, how you are converting it? 50 kilometer multiplied by 1000, you will get 50,000 meters, and divide by 60 by 60, you will get in per second. Okay. Densities here is given as kg per meter cube, so no need to convert it. Just simply apply in this formula. So your lift force will be equal to 0.75, 2.25 multiplied by 1.15 multiplied by u infinity ka square and 13.89 square divided by 2. So this will come out as your 187.20 Newton. Okay. Next point is drag force. How you are going to calculate drag force? The simple formula is CD multiplied by area rho v square by 2. Here CD is given as your 0.15, area is already you have calculated 2.25, and rho will be equal to your 1.15, u will be equal to 13.89 square by 2. Simple. So what you will get? FD as 37.44 Newton. Okay. The third question was the resultant force. How you are going to calculate the resultant force? Is simply Fr will be equal to root over FD square plus FL square. Okay. So FD you have just calculated 37.44 and FL was 187.20. Okay. So what you will get the resultant as 190.85 Newton. Okay. In this equation, you can realize that FD is 37.44 and FL is 187.20. That means that lift force is actually the on particular flat plates is more than very more than FD. Okay. The drag force is very much less. So you can say the flat plate must be in a position that that drag force is very less and lift force is coming more. Okay. So here you can get the resultant of 190.85. Now the next point is the power required to keep the plate in motion. Okay. So power required to keep in motion, the formula is very simple. Force in the direction of motion multiplied by velocity. Okay. When we divide it by 1000, you will get in kilowatt. So force in the direction of motion, that means you are talking about what? FD. And velocity, obviously the streamline velocity or u infinity you can say. FD you have already calculated as 37.425 and your u is 13.89 divided by 1000. So what you will get? 0.519 kilowatt. Okay. So this is actually a simple question when all the parameters was given. Okay, area was given, velocity was given, density was given. Just you need to put on formula and you can get an answer. Now second question, experiments were conducted in a wind tunnel with a wind speed of 50 km per hour. Okay, on a flat plate of size 2 meter long and 1 meter wide. Now this time your area is like 2 meter by 1 meter and density of air is given as 1.15 kg per meter cube and the wind speed is given as 50 km per hour. Okay. On a flat plate of size, the density of air is given. The coefficient of lift and drag is also given. The coefficient of lift CL will be your 0.75 and CD is your 0.15. Okay. So determine the first lift force, second drag force, third resultant force, fourth is direction of resultant force. Okay, this point is somewhat new than the previous question. The fifth point is power exerted by air on the plate. Okay. So how you can solve it? See, the solution is here. Area of plate will be your 2 meter square. Okay. Then the velocity of air is given as 50 km per hour. See, this is an situation. Okay, let's go to the question again. This is a situation when the experiments are conducted on a wind tunnel. Okay, say when you are experimenting, okay, wind tunnel, okay, wind tunnel in the case of this simple experiment, okay, when all the other parameters are given. So whenever this kind of questions comes, do not get confused. This is simple and situation, but other parameters are also given. So velocity of air, you can say, is 50 kilometer per hour. You can convert it on meter per second, 13.89 you will get. Okay, the density of air is 1.15. Value of CD and CL is already given. So the how you can solve it? Simply apply formula for FL, CLA rho U square by 2. What you will get? 166.404 Newton. Okay. Now the second is drag force. How you are going to calculate drag force? CD multiplied by area multiplied by rho U square by 2. Here CD is already given as 0.15, area is 2, and rho is 1.15, and U is your 13.89 U square by 2. So what you will get? Drag force as 33.28 Newton. Now the third question was to find out resultant force. So we know very well how to calculate resultant force is simply root over FD square plus FL square. Okay, you can get it as 169.67 Newton. And the direction of resultant force, this was the fourth point. Okay, so the fourth question was direction of resultant force. How you can get the direction of resultant force? By this formula, tan theta equal to lift force divided by drag force. So lift force you have calculated as 166.38, and the drag force was 33.275. So what you will get as tan theta equal to 5. So theta will be equal to here 78.69 degrees. Okay. So this is the direction of resultant force with the horizontal. The fifth point was simply power exerted by air on the plate. So the power you can calculate is as force in the direction of motion multiplied by velocity. The force in the direction of motion was Fd. Okay, Fd you have calculated as 33.28, and the velocity was 13.89. Okay, this is coming as 462.26 watts. Okay, when you divide it by 1000, what you will get? An answer in kilowatt. Okay. So that's all for today. We'll continue this lecture on next lecture. Jai Hind.